Hi guys. We will solve some problems from the first worksheet. Okay, we will complete the first one and then we will continue from the second one. Okay, to the question 6. We will solve some questions I marked. All right. Let me write the question first. So we will use chain rule to find dz over dt. Okay, for the given functions. I will solve the first part. So we're given z equals to x squared plus y squared plus xy, where x equals to sinus t and y equals to e to the t. All right. So how can we use that chain rule? So look at the function z. So z depends on x and y, and both x and y are dependent on t. So you need to write dz over dt as follows. Dz over dx, then dx over dt, plus dz over dy, dy over dt, right? Now, what's dz over dx? So z is given here in the question. We will use that equality. So it is 2x plus y. This is dz over dx. And what about dx over dt? X is given here. We will use that. So the derivative of x with respect to t is cosinus t plus, now dz over dy. Again, go back to this equality. So we get 2y plus x. Now dy over dt is e to the t itself, right? Here we have y. So we get this. Again, the same question. Use chain rule. Now to find dz over ds and dz over dt now. We will solve the part B. Z is given by sinus theta cosinus phi, where theta is equal to st squared and phi is equal to s squared t. Okay, you see z is dependent on phi and theta, right? So phi is dependent on s and t, theta is dependent on s and t. Now dz over ds, let's first find that. Dz over d theta, then d theta over ds plus dz over d phi, d phi over ds. Now dz over d theta is, here we have sinus theta. So you take the derivative with respect to theta only and get cosinus theta, cosinus phi. You see this value as constant, right? So that's why we have cosinus phi as multiple times. Now we need to compute this one, d theta over ds. You see theta is given by this value, st squared. So the d theta over ds is equal to t squared. We have this plus dz over d phi, which is sinus theta minus cosinus minus sinus phi. Now the phi over ds, phi is given by this, and the derivative of this one with respect to s is 2st. So you have 2st, and we're done. Now t, you have the same, you start with the same, then phi over d t plus dz over d theta over dt. Okay, now first we take the derivative of z with respect to phi, which gives you minus sinus theta sinus phi, and then d phi over dt, phi is given here, so you get s squared only, plus dz over d theta, it is cosinus theta cosinus phi, times d theta over dt, theta is given here, so you get 2st, and you're done. And the last question of this worksheet, we will write the chain rule for the given case, it says. Okay, let's write only for x. We have 3 functions in the question. We will solve it only for x. Okay, the function x is dependent on r, s, and t. Okay, so how can we write the chain rule for this function? So you see, it depends on r, s, and t, right? Okay, it depends on r, s, and t. Sorry, I wrote the question wrong. Now I get it. We have 3 functions. The first one is dependent on x and y. So the first one is u, which is f of xy. Then x. X is dependent on r, s, and t. And the last one, y. And it's dependent on r, s, and t again. Okay. Now we will use the chain rule to write the derivatives. So you have first, you see u is dependent on x and y, x is dependent on r, s, and t, the same valid for y. So du over ds, for example, du over dx, and dx over ds, plus du over dy, and then dy over ds. So as you can guess, du over dt then equal to du over dx, dx over dt, plus du over dy, dy over dt, right? And finally, du over dr, du over dx, dx over dr, plus dy, dy over dr. Okay. Well, this was the last question of the first worksheet. Now we will solve some questions from the worksheet 2. I will write the questions again. So the first one, find the directional derivative of f at the given point. Okay, in the direction indicated by the angle. Okay, now we will solve the part B. F of xy is given by this. The point is 0, 0, and the angle is this. Okay. Now we write, so it's given by this, right? DUF at the given point 0, 0. If you say the vector direction vector u, then you will find this. Okay, you will find the gradient at the given point. So let's look at first the gradient of f. Okay, which is, you find the derivative of f with respect to x for the first component, which is e to the x cosinus y, and as f sub y is minus e to the x sinus y. You just take the derivative with respect to coordinates. Okay, first x, then y. So at the given point 0, 0, you get what? E to the, you just plug x equals to 0 and y equals to 0. E to the 0 is 1, cosinus 0 is 1, so you get 1 in the first component, and for the second one, sinus 0 is 0, so you get 0. Okay. Now, what about the vector u? It's given by cosinus theta and sinus theta. Cosinus pi over 4 is equal to square root of 2 over 2, and sinus pi over 4 is the same with cosinus, so you get this value. Okay, thus duf of 0, 0 is equal to this dot product. So you have this value times 1, 0. Okay, you multiply them point-wise, component-wise. You take this 1 times 1 plus this times 0, and you get this. Okay, this was the first question. Now the second one, find the gradient of f and then evaluate the gradient. I write it briefly at the given point P, then find the rate of change of f at P in the direction of the vector u. Okay, we will solve part B. We're given f of x, y, z as follows. And the point P is this one. And u is this vector. Okay. Now, first we will find the gradient of f. Okay. So it's f sub x, f sub y f sub z. Okay, now you take the derivative of f with respect to x, 2x yz minus yz cubed. And for the second component, you take the derivative of f with respect to y, which is this. And finally, with respect to z, okay. So we're done with the first one. Now for the second one, we just plug the point P there, which is this point, okay. You just plug x equals to 2, y equals to -1, and z equals to 1, which will give you, let me write directly, this value, okay. So we're done with this. And for the second, for the last part, you just find this value again at the point P. So it means this, okay, at the point P. Now u is, where is u? U is 0, 4/5 minus 3/5. And the gradient of f at the point P is, we just computed that, is this. Okay, again, dot product, you will get 0 times -3 plus 4/5 times 2 plus -3/5 times 2. And you will get 2/5. Okay. By the way, here the given vector u is already a unit vector, right? If you compute its length, you will find what? Square root of 0 square plus 4/5 square plus -3/5 squared. So you will get 25/25, which will give you 1. So it's a unit vector. That's why we directly took the vector u. Okay. If not, you can divide the given vector by its length. So in this case, the vector you will obtain is always a unit vector, right? But here we didn't need that because the given vector is already units. And the third question, again, find the directional derivative of the function at the given point in the given direction. Okay. We will solve part B again. We're given g of PQ defined by this. And the given point is 2, 1, and v equals to I plus 3j. Okay. Now we check if the given vector v is a unit vector. You see it's the vector 1, 3. And the length of v is then 1 squared plus 3 squared, which will give us the square root of 10. It's not 1, so v is not a unit vector. As I said before, we can obtain a unit vector using v. So let u be as in this form, v over the length of v. Okay, so we had before this vector, we divided by its length. Okay, now component wise, we have these values. Now if you check, you will see it's the unit vector. You don't need to compute that using that numbers, actually, you have this vector, right? So the length of this vector is given by this, and it's equal to this, so you get 1, which means u is a unit vector. All right. Now, what do we do? We will find the gradient of g. Now, g sub p, g sub q, we need to find. Okay. You get, in the first component, you get this value times this, and in the second part, you get 3p squared q squared. Okay. So at the given point, you get what? 28, comma minus 12. All right. We have then, let's say PG of P. Okay. What do we have? U dot product G, the gradient of G at the point P. So we have 1 over square root of 10, 3 over square root of 10 times 28, comma minus 12. You multiply them component wise. 48 over square root of 10. So you get this. Okay. Now this was question 3. Now we will solve the question 4 now. Find now we're given this function. The point is 1, comma minus 1, comma 3. The direction is this point. So you're not given a vector, but a point, a direction with a point. So you will write your vector yourself. All right, let's find first the gradient. F sub x, F sub y, F sub z, y plus z, x plus z, and finally y plus x. So at the given point then, we have what? 2, 4, 0. Okay. Now you need to write your vector, the direction vector. So let you, now you write it as in this form. Okay, so you have what? So we write it as in this form. 2 minus 1, and 4 minus minus 1, 5 minus 3. Okay. So what do you have? 1, 5, 2 over square root of this. And there you get 25, 29, 30. Okay, hence you have now the vector u is here. We have dot product. What did we have? 2, 4, 0. Okay. Now the first component is 1 over square root of 30 times 2 plus 5 times, I said 1 over, sorry, 1 over, oh yes, 1 over square root of 30 times 2, 5 over square root of 30 times 4 gives us this, and the third component we get 0. So you have this. All right, last question. Find equations of tangent plane and B, the normal line. All right, we will solve part A of this question. Okay, we have 2 questions. They're also called as A and B. Okay, and in the first part, we're given this surface. And the given point, let's say P, is this. Now, let's, so we will find the tangent plane. For that, we need a normal vector first. So how do we find it? First, let this one, f of x, y, z, equals to this given function minus 10. And the normal vector is given at the given point is given by this gradient at P, right? First find the gradient. So f sub x, f sub y, and f sub z. Now you have, it's enough to compute on here, right? So you have 4 times x minus 2 times the inside function's derivative, which is 1. So you get 4x minus 8. And for the second one, you get 2y minus 1 and 2z minus 1. Sorry, I wrote here 1, but it's 3. Yes, the rest is the same. And we have 3 here. Okay. So at the given point, we get what? Let me write directly. X equals to 3, so we get 4. 3 minus 1, 2, 4, and 2, 4 again. Okay. This is the normal vector. Now we write the equation. Let me write here. Hence the tangent plane equation at where at P is, now you write, so you write as follows. You write the first component of the normal vector times x minus p0, which is this, x0, which is this, plus again 4 times y minus now this one, plus 5 times, sorry, not 5, 4 again here, times z minus 5. Okay, is this. All right, or equivalently, you can say if you want. So 4x minus 12, let's compute here. 4x minus 12 plus 4y minus 12 plus 4z minus 20 equals to 0. So you have in the parentheses of 4 equals to what? Minus 24, 44, sorry, equals to 0. So you have, if divided by 4, x plus y plus z minus 11 equals to 0 is the desired equation. And what was the other question? So we will write also the normal line equation. Okay, so to write an equation for a line, you need to know, so let's say this is the line that we want to write its equation. So you need a directional vector on it or parallel to it, okay, one of them. But in our case, normal vector is already on the line, so we already have that vector, and you need a point on it, which is P already, so you just directly write the equation, okay. So the normal line equation is then, so the point is here, P, 3, 3, 5, plus T, any real number, times the vector, which is the normal vector for 4. Okay, you can write, if you want, parametric equations again, or equivalently, you can write x, which is 3 plus 40, and 3 plus 40 again, and z, 5 plus 40. Okay, if you want, you can write it as in this form, and you're done. Okay, so we had a plane. Sorry, we had some surface. We had some surface. Let's say this. Okay, we had a point on it. Let's say P. We found a tangent plane equation. We wrote that. Okay, this is the tangent plane, let's say. It continues like this. It's a plane. Okay, it touches the to the surface. Okay, so this is the tangent plane, and we then find a normal vector which is orthogonal to that. Okay, this is the normal vector, which is here. Let's say n. And then we find the line passing through that vector. Okay, so the line again is orthogonal to the plane, the red one. Okay, we found the equation of this black line here, right? Okay, we're done. We will next week continue from the question 6, face to face, of course. See you.